Hello. Just waiting. Can everyone see all right? All right, nice. So we're Morpheus, and I'm going to be presenting about our brainboard, which is an alternative electronic solution. So let's just, I guess, some quick introductions. I'm Brianna. I'm a senior at Jumpstart. This is my 4th year in FRC.
I'm Gabe. I'm a junior, and this is my 2nd year in FRC.
My name's Isaac. I'm a junior in high school, and this is my 2nd year doing FIRST Robotics.
My name is Aditya, and I'm a freshman, and this is my 2nd year in FRC.
So we're going to talk a little bit about a major problem when building a robot. And this is electronics. They take up a ton of room on your robot where you could have put an important mechanism, and that can limit design options for your mechanisms. You then also have to place your mechanical system in a position that can make it difficult to access the electronic components.
So yeah, here is an example. The electronics on this robot take up a lot of room that could have been used for mechanisms.
So here's another example. This is our 2019 robot. As you can see here, our electronics are on the superstructure, and when we had to add the climber, we had to actually drill a hole through the electronics board in the middle of an event, and we had to move around electronics to make that happen. And so this is just a problem with electronics because they can interfere with mechanisms.
So this is a picture of the Cheesy Poof's 2017 electronics, and it's a hopper on a hinge. It is one solution to this problem, but it is tricky and complicated as the wires on the pivoting mechanism must be constrained in both of the positions. So the first picture is of our 2017 robot's electronics, and as you can see, the electronics are right in the middle of the robot, and the game pieces need to move around them constantly. This makes the electronics more susceptible to damage by the game pieces.
So for 2020, we found that we needed more room on top of our robot. And so it was essential to place the electronics components underneath the robot, out of harm's way from game pieces, as well as from accidental damage from other robots.
So the electronics all fit within the drivetrain area, and this is an important improvement as it leaves a lot of room in the rest of the robot for other important components.
So the wires are all bundled together at common points. We have a lot of wires running. So then we drill holes through the board, like this one here, that can run a bunch of wires to and from the brainboard and the rest of the robot.
So the wires should also be properly fastened to a part of the board where it's removed from any possible contact from moving parts.
And because of the electronic's small size, they all fit within a 2-inch height parameter. However, if you have a pneumatic system on your robot, you'll have to place the components outside of the brainboard.
Okay, so what is the brainboard? Brainboard's an effective solution for the placement of electronics, and it contains all the electronics while not sacrificing valuable space for other mechanisms on the robot. The board is upside down on the robot's drive base, and while this may seem strange at first, it provides easy access to components and gives plenty of space for all the electronics. This image is of a Citrus Circuits 27 robot, and as you can see, their model is upside down and the electronics are on the bottom of the robot. So our robot's electronics board is inspired by this.
So how does it work? The brainboard design is fairly simple. The main electronic components are secured to a board. This board is then placed on top of the drivetrain with the electronics facing the ground. A removable plate is placed over the electronics to keep them safe while the robot is being used, and then holes are drilled on top of the board through the wood to run wires in and out of the brainboard. So for organizing the brainboard.
Okay, so for the motor controllers and PDP, we actually attached these using plastic screws that could be easily cut flush with T-nuts. And PDP needed to be near the battery since it gets power from there, and the motor controllers should be kept near the PDP for easy connection. And you should also be thinking about where each mechanism is relative to its assigned motor controller.
So for the pneumatics, as you mentioned before, a lot of pneumatics parts don't fit inside the brainboard. The compressor is a bit tall to fit in our current design, and the solenoids as well. So they had to be moved to the outside. Because of this, the placement of the pneumatic control module became really important, so that the wires could reach the solenoids because they are pretty short. And the air tanks were also added outside of the main brainboard component.
So now for the RoboRio and voltage regulator module. So the RoboRio is the brain of your robot, and it's super important that it's placed in a good position. It should also be centered so that the gyroscope is as accurate as possible when the robot is tilted. The voltage regulator module, or VRM, is less important to position because it's much smaller than the RoboRio, and so you can put it just about anywhere.
So for the radio, we place the radio above the brainboard for easy access, and this allows for a good radio connection with the laptop and the FMS, and it makes it easy for us to remove and add during competitions when we program the radio. It also makes it easy to tether with the robot via Ethernet.
So here are the pros and benefits of having a brainboard. The brainboard is an aesthetically pleasing feature of the robot, as well as a protective one. It allows you to keep all of your components safely underneath the robot, avoiding accidental damage from other robots. It also allows for more freedom to build when assembling the top portion of the robot.
Although using a brainboard has a lot of benefits, using a brainboard can make it harder to access the components, especially during the competition. It is not advised to use in rough terrain games because there's a chance that something could puncture the belly pan and damage the electronics. It can also be harder to add some components due to size constraints, and it takes some initial planning to do it right. But in our experience, the rewards outweigh the negatives.
Okay, so for tips, there are some things that you should be aware about when implementing the brainboard into your robot. All wires should be properly secured using either high-strength tape or zip ties or something similar. And it should be mentioned that the electronics will most likely be shaken during driving, and securing the electronics properly is top priority. If a component should become disconnected and fall off, it could create serious damage both to it and neighboring electronics. And if something should happen, you want the electronics board cover easily accessible. You shouldn't have it improperly secured, but it's important that it is easily taken off in case of an emergency. The board should also be supported so that it does not warp, and refrain from securing any moving parts to the board unless attached elsewhere.
So we're going to go over some of our specific choices that we made when we designed our brainboard implementation.
So for the mounting board for the electronics, we used wood because of how pliable yet durable it is. And when drilling holes for screws on a wooden board, wooden shavings won't short circuit electronics like metal shavings would. A wooden board also allows for quick and easy changes to the board without a need for large machinery, as would be needed for a metal board. It's also cheap and lightweight.
So we also used plywood for the cover, and we used the wood to cover the electronics from any damage, and while driving, we ran over quite a few game pieces without much trouble. The smooth property of the wood saved us from getting stuck, while this seemed to be a serious problem for other teams. We had originally considered using Lexan for the cover because the electronics would be visible, but we decided against it because of the lack of rigidity and we didn't have any support in the middle for the cover. Static charges can also build up on Lexan and damage electronics.
So we also use a radio on top, and we use it for a couple of reasons. It allows us to connect to the robot easily, and it also helps with the signal strength.
Yeah, so we used plastic screws for all of our electronics. And so we had T-nuts that we put into the wood, and then we had these long plastic screws that we screwed into the threaded inserts that are embedded from the opposite side. And then we cut off the ends of the screw so that they were the right fit and were flush with the top of the electronics board. So mechanisms could be placed right on top of it without worrying about screws or nuts making it not flush.
So for our belly pan or cover for the brainboard, we have it secured using small screws called tap tights. These screws are really easy to put in and really easy to take out. This is especially important during a competition when you need to make a quick change, repair, or need to add something to the brainboard. You only need about 6 screws for a secure fit, and having so few screws allows you to quickly remove and insert the belly pan. If the screw hole threads wear out from use, there are plenty more screw holes to tap.
So how do you find out if the brainboard is the right solution for you? The brainboard is not the perfect solution for every team or every game. Each team has its own unique style and capabilities, so it's really important that you know what makes sense for you and your team. If your designs take up a lot of volume on your robot, this design can help you save much needed space. If you have access to CNC tooling, creating the board is fairly simple, although it's quite possible even without these tools. If for the game, it makes sense that you maybe don't want to have your mechanism accessed from the top, but instead the bottom, then I would definitely suggest it. If you're a team who's tired of waiting until the last minute and just throwing on electronics wherever there's room, a design like the brainboard and a little bit of planning can really go a long way and save a lot of agony later on. So here's just some component information for the plastic screws and the T-nuts that we use to connect our electronic components. And so yeah, does anyone have any questions for us? Any questions about our brainboard, about design? Feel free to ask them now. Let us know. I'm looking in the chat now, so. Yeah, like I said, definitely. Well, we're still here if anyone is curious about what design. Right. And then also we just want to give a tribute to Woody Flowers. He was a great leader, a great mentor, and a great friend, and you're still saddened by his loss. All right, so this is a question. Do we need to recalibrate the gyro because it's upside down? Yeah, so you're going to want to calibrate it in whatever, like, I guess, orientation, even if I set up it sideways. It depends what gyroscope you use, exactly how you would go about it. We use the Navex with a lot of success. And there's a way to essentially ground it when the board was when it was connected to the board. And so it's always a good idea, regardless of your configuration, to make sure that your gyro is calibrated for whatever you're using. And you also want to make sure that it doesn't really matter if it's upside down, right side up, but you don't want it at an angle. So you don't want the gyroscope like tilted like this, because then it has a lot of issues. Whereas if it's flat or if it's upright, it's a lot more flexible that way.
I think, Brianna, the coordinate system has to be flipped in the software. That's all that has to be done, right?
Okay.
I think you guys did that, but maybe you forgot about it.
Yeah, well, we used two different gyros at one point. We did the Navex, and there was another one. One of them we had to flip. If I remember correctly, we did not have to flip the other one. So I would just definitely check the documentation for the individual gyroscopes you use to make sure that you know exactly the orientation.